Alright, so this is a video on Newton's second law. We have a mass M resting on a frictional horizontal surface, and this mass has a force F being applied to it. So the questions that are being asked is, what force is required to move the block? What force is required to keep the block moving? And what is the distance d? Okay, so we are given the mass, we're given the static coefficient of friction, and the kinetic coefficient of friction, and also an initial velocity. So let's start out by solving A. Let's do the free body diagram for this mass at rest. We have the gravitational force going down, we know that's always the case, and a normal force in opposing it, because that's the force that this surface is applying onto the mass to keep it in place. And we know that there is a force F being applied in the positive x, with those being our axes. And because it's at rest, we know we're dealing with static friction. So because the force is being applied on the right side, or to the right side, static friction is opposing that, is trying to keep the object in place. So how can we solve for static friction? Let's first do our sum of forces. Our sum of forces in the x equals the negative static friction force plus the force applied, which equals NA. Now let's do the same for the y. The sum of forces in the y equals the normal force minus the gravitational force. And that also equals ma. I forgot to mention in the beginning, but this is a constant velocity problem. So because of that, both of these terms go to zero, because we're not dealing with any acceleration. Okay, so how can we solve for the static friction force? Well, we know that static friction force is less than or equal to the static friction coefficient times the normal force. The reason it's not completely equal to it is because for all values of the force being applied, up to a certain value is your static friction force. So once you get up to that value, your static friction converts into kinetic friction, which is why it is a less than or equal to sign. So how can we solve for Fs? We have our sum of forces in the y, N equals Fg. All I did was bring over the Fg. So we know that Fg is just mass times the gravitational constant. So our normal force is 50 kilograms times 9.81 meters per second squared. And this equals 490 newtons. Okay, so we know that our static friction force is for all values up to that value. So let's plug in Fs is less than or equal to mus, which is 0.2, multiplied by the normal force we just found, which is 490. And we know that that is 98 newtons. So for the force applied to need to get the block moving is 98 newtons. You need to apply 98 newtons of force to overcome the static friction. That'll get the block into a kinetic friction. Okay. So let's do the same thing for D, the force required to keep the block moving. So this is dealing with kinetic friction. Let's do our free body diagram again. We have the force of gravity acting downwards and the normal force opposing that. And we know that we have the same force being applied to the right, but instead of static friction opposing it this time, we have kinetic friction. Kinetic friction always opposes the motion of your mass. So if your mass is moving in the positive x, kinetic friction is acting against it, trying to slow it down back to a rest state. So let's do our sum of forces. In the x, we have the negative kinetic friction force plus the force applied equals these go to 0 because we're dealing with constant velocities. So what does Fk equal? The kinetic friction force equals to mu Kn. The reason it's an equal and not the less than or equal like the static friction is because there's only one force needed to get this thing moving, and that you just need to maintain that. So let's do the same thing we basically did the last problem. Let's solve for N, because we need N in this equation. N equals the force of gravity, which is equal to mass times gravity. So our mass is 50 kilograms, multiplied by 9.81 meters per second squared. So what does this give us? This gives us 490 newtons. Again, it's the same normal force as the first example, because nothing's really changing in that sense. So for Fk, we get mu k, which is given, our coefficient of kinetic friction is 0.1 multiplied by 490 newtons. And this gives us that our kinetic friction equals 49 newtons. And this makes sense. If you remember, so this one was 98 newtons, this one is 49 newtons. This makes sense because it takes a greater force to overcome the static friction. And this is because the static friction coefficient are always greater than that of kinetic coefficient of friction. So it always takes a greater force to overcome that static and get it moving. But once you get it moving, it's always easier. It makes sense because whenever you're moving furniture, when you're first pushing up against that cabinet, it takes a greater force to get it moving. But once you have it moving, it kind of flows. It moves smoothly. So our kinetic friction is 49 newtons. For part C, it's asking what is the distance d that this mass travels after the force is applied. So after the force is applied, we're not pushing it with a constant velocity anymore. The frictional force is going to be causing our object to slow down. So we got to find the acceleration in this case. So let's do our free body diagram again. We have the gravitational force acting in the negative block, and we have the normal force opposing that. It's keeping the block in place. But now instead of a force being applied that way, we don't have that anymore. Our block has no force being applied to it. It just has a kinetic friction slowing it down. So let's do our sum of forces in the x. We have the negative Fk equals ma. And in this case, because we have an acceleration, we can't take this to be 0. We have to solve for a. So dividing by m, we get our a equals negative Fk divided by m. And we found our kinetic friction force to be 49 newtons. So our a equals 49 newtons divided by 50 kg, 50 kilograms. And this gives us that our acceleration is 0.98 meters per second squared, or negative 0.98, excuse me. So this makes sense because as our block is moving along, this negative acceleration is causing it to slow down. So let's find out what our d is. We're given an initial velocity, and we know that once this block reaches d, it's at rest. The block has completely slowed down due to friction and is at rest. So let's use our kinematics equation. Vf squared minus v naught squared equals 2ax. Alright, so we know that this is 0 because our final velocity is 0. So we get 0 minus v naught squared equals 2ax. And our initial is 5 meters per second. So this negative won't matter because we're squaring. We're going to get 25 meters per second equals 2 times 0.98x. We're putting in the 0.98 for our a in this case, of this equation. So 2 times negative 0.98 equals negative 1.96x. And we still have our 25 meters per second on this side. So let's bring this out here. We have 25 meters per second divided by negative 1.96, and that equals our x. In doing this calculation, we find that our x 12.75 meters. So after this force, this 49 Newton force is applied to our mass, it will go 12.75 meters before it completely comes to rest. And this is because the friction is causing it to slow down. So we found out the force that is required to get the block moving. This was dealing with static friction. So we solved for static friction, which was greater than the kinetic, which made sense. We solved for the force required to keep this block moving, which was 49 newtons. And then we found out that once this 49 Newton force was applied, how far will this block slide along? And we found that it was 12.75 meters.